Okay, I see only one student, Sri Nivedita. We'll wait for a while. Oh, suddenly I see so many people. Okay, cool enough. So, I hope all of you are ready, right? So, I think today it is electrochemistry, only electrochemistry. And last class we couldn't complete colloids, right? So that alone we'll just see for 10 more minutes, 10 minutes, 15 minutes, and we'll continue with electrochemistry, right? Okay, so is there any specific questions you want to ask regarding colloids, or I'll just ask my questions and I myself will get to know what you don't know, and accordingly I'll teach. Is there anything specific? Okay, fine. So colloids is what we are going to see, and yes, I got a new marker. Wait, I'll just open it. Okay, right. So colloids, right? Okay. So we know, right? If I take matter, right? We know what is matter. Right? Matter is something which occupies space and has some mass, right? Okay. So this matter can be divided into two categories. Can you tell me what are these? Matter can be obviously one way by which I'll be able to classify matter is in terms of its phase, solids, liquids, and gases, right? So what is the other way of classifying matter? Yes, what is the other way of classifying matter? There are two types by which we'll be able to classify. Can you tell me what are they? Nobody knows. Okay, so matter like this you would have studied in your ninth class, if you would have remembered. So one is what is called as pure substances, and the other one are what are called as mixtures, right? Okay, so what do you mean by pure substances? Pure substances are going to be made up of single entity, right? Only one type of particular entity is going to make up these pure substances, right? So this single entity which you're talking about, right? So this single entity can be either atoms or it can be molecules. That is two or more atoms combining together to form a molecule, right? So based on which is that single entity, right? We will be able to classify them as your elements, compounds. Obviously, you understand that in elements, the single entity which you're speaking about is atoms. Sodium element means only sodium atoms. Carbon element means only carbon atoms, right? So same way for compounds, say ammonia compound will be made up of ammonia molecules. So many molecules will be there, right? So here, these are molecules. Here I have atoms, right? So now when I go to mixtures, right? So mixtures, how will I define them? It is just made up of two or more pure substances, right? Two or more pure substances. Now you can ask me, sir, say compounds are how are they formed? Compounds are generally formed by combining two or more elements. Again, these elements are pure substances, right? So how compounds are formed? Compounds are also formed by mixing, adding two or more pure substance. That is, in this case, would be elements. So what is the difference then between a compound and a mixture? Both element?
Sir, in compound,
Yeah,
the proportion is fixed, sir, but in mixture, it's not. Proportion
absolutely.
of the.
Right. Correct. I understand. Correct. Right. So the thing is, if you want to make a mixture, right, how much you add, like the amount of pure substance you're going to add doesn't matter. You can add how much over you want, right? But in case of compounds, you know they have to follow the laws of chemical combinations, right? Law of conservation of mass, law of constant proportions, law of multiple proportions, so on and so forth, right? So as he said, the proportion, the ratios in which they are mixed, the masses of the ratios in which these elements are mixed is constant. Like for example, in H2O, we know it is going to be 2:1, the ratios in terms of the number of atoms, right? Okay, but in case of mixtures, those things doesn't matter, right? Okay, now these again can be classified into two more. One is what is called as homogeneous mixtures, the other one are what are called as heterogeneous mixtures, right? So homogeneous mixtures, we know, like they are going to have the same concentration throughout the solution or throughout the mixture, right? Say okay, so we don't have to go into the details. Homogeneous mixtures, they go on each and every point in the solution or in the mixture, the concentration of all these components are going to be same. The amount of component present in each of these points is going to be same, right? But that is not going to be the case in the case of heterogeneous systems. At each and every point you might have different concentrations, right? Any doubts? Someone, I think, is okay, cool, right? So in heterogeneous systems, I'm not going to have constant concentration on all these points, right? So example of homogeneous systems are what is your solutions. Again, you have a chapter on that, right? True solutions, right? So again, it's like we'll talk about it more when you go for solutions chapter. In heterogeneous systems, there can be two examples, right? One are what are called as suspensions. What is suspension? A sand and water, oil and water. Oil and water, I can sometimes call it as colloid, but still sand and water is a better example, right? So that you can see that it is not obviously at the bottom sand is going to settle, at the top layers you'll have lesser amount of salts, sorry, sand, right? Other one is what is your colloids, right? So basically a colloid is a heterogeneous mixture, right? Colloid is a heterogeneous mixture, that's what you need to understand. Okay, right. And as we like, it is very similar. It is actually very similar in a lot of ways with respect to true solutions, right? Fine. So what you have to understand is about the particle size, right? So if I compare the size, right, your suspensions are going to have very huge particle size, and then comes your colloids, and the least are going to be what is your solutions, true solutions, that is your homogeneous mixtures. Okay, right? So there is several different books will give different particle size range for all of these, but generally we say that for colloids it's between 1 to 10 nanometer, right? 1 to 10 1 to 10 nanometer, or different books says different thing, but you don't understand it is in the nanometer range. Nanometers 10 to the power minus 9 meters. Okay, so colloids are going to be in this what is that particle size range. Okay, so suspensions will be able to see with the naked eyes, we know that, right? Colloids and solutions you will not be able to see them with the naked eyes, all you have to use a microscope, right? Actually speaking, true solutions, even if you want to visualize the particle with a microscope, sometimes it is very difficult. Like not all microscopes will be able to, you need to have a very powerful microscope, right? But colloids, not an issue. Even with a small, like good enough, decent microscope, I'll be able to visualize or image your colloidal particles. Okay, right. So fine. So like, what are these made up of? What are colloids made up of is the next question, right? As I told you, it is some way similar to your true solutions. We know that I'm going to have, just like you have solute and solvent, right? Here I'm going to have dispersed phase and dispersed medium, right? So dispersed phase is what is considered like, it is like, you can analogous, it is analogous to solvent in a solution, dispersed phase, right? And dispersed medium is like your solute, but again that pretty much doesn't hold good every time, but still you can consider it like this. Okay, dispersed phase means solvent, dispersed medium means solute. Okay, so now okay, we understood what are colloids, what are these made up of. Okay, right? Next thing what you have to understand is what are the different types of colloids. Okay, so for understanding different types of colloids, you have to take different concentrations, different parameters for you to classify, right? Say first classification is going to be based on what is the phase, or in which phase these dispersed phase and dispersed medium are present, solids, liquids, and gas. You can have so many combinations, right? Say for example, if you have a dispersed phase to be a solid in liquid, dispersed medium is liquid, so then you're going to call it as sol, right? So there'll be a in the inside textbook you'll have a table, right? You'll have a table saying dispersed phase is phase, dispersed mediums is phase, what is the name of the colloid and its example. That table is very important. Lot of times 1 mark questions and 2 mark questions can come from that. Okay, that table is very important, please mark it. Okay, so like then you have liquid, it's called liquid sol. Say a gas in solid is what is called as foam, right? Gas in gas is what is called as aerosols, right? So you have to know what are the other like for each and every category you have to know what is the example also. Okay, please make sure you know it, at least 1 or 2 examples per type you should know. Okay, right. So that is the first classification. Second classification is going to be based on how are these colloids formed, right? So based on that only you have multimolecular colloids, associated colloids, macromolecular colloids, and all so on and so forth, right? So you just have to understand that multimolecular means so many molecules will come together. Macromolecules means one macromolecule is enough, that is going to give me the colloidal particle size, right? Associated means again like too many say a smaller amount of smaller aggregates, small aggregates will be there, already they are clusters, already they are made up of number of substances, again they will come together to form associated colloids, right? So based on how they are formed you have 3 types: macromolecular, multimolecular, and associated colloids. Okay, fine. Next thing is about how do you, okay, any other classification? Yeah, definitely, right? I have one more classification depending on what kind of interaction is there between your dispersed phase and dispersed medium, right? So based on that we know how are you going to classify. How is it classified? Based on what type of interaction is between dispersed phase and dispersed medium. What are the classifications? Yes, depending on the type of interaction between the dispersed phase and dispersed medium. What are the two? There are 2 types. What are the 2 types? Yes, you should know it. How come you don't know it?
Hydrophilic and hydrophobic, sir.
Okay, hydrophobic and hydrophilic. Okay, so like hydrophobic is where I have the solvent or the dispersed state maybe to be water, but in general they're going to be lyophilic and lyophobic, right? So if you just remember the names, right? I have lyophilic and lyophobic colloids. So I think from the name itself, you'll be able to understand what are they. In lyophilic systems, lyophilic colloids, the dispersed phase and dispersed medium love each other. They have very strong interaction. They have very strong attractive force acting between dispersed phase and dispersed medium, right? But in lyophobic, it's exactly opposite. The dispersed phase and dispersed medium are going to hate each other. That is, they're going to repel each other, right? So obviously comparing if owing to stability, right, we can obviously see that lyophilic colloids are going to be more stable than the lyophobic colloids, right? Lyophobic colloids are relatively very unstable, right? So sometimes what you do is you want to stabilize the lyophobic colloids. So what you do is you add lyophilic colloids as stabilizing agents. Okay, there is something called as stabilizing agents. So stabilizing agents are going to stabilize the lyophobic colloids. And what are these what are these stabilizing agents? These stabilizing agents are nothing but some other lyophilic colloid, which is going to stabilize the lyophobic colloid. Okay, right. So these are all the classifications of colloids. Right. Now, next thing is how do you prepare them, right? So how do you prepare them? There are various chemical methods. Please look, like you just have to read the NCRT for this chapter. Let's read it line by line. Just mark the important point. That's all you need to do. That's what even I am doing. I'm just making sure that I just give you an overview. Okay, so what are the methods of preparation? You have chemical methods, right? So in chemical methods, what you're going to use chemicals, you're going to mix them in equal proportions or some proportions in suitable conditions of temperature and pressure, right? You will be able to get gold salt, silver salt, arsenic chloride, arsenic sulfide salts, right? Salts. I'm not talking about SALTS. No, I'm talking about SOLS, salts, colloids. Okay, so those, the first one is by chemical methods. Second one is by your Briggs arc method. So hope you know this, right? Briggs arc method. It's very simple, right? What you have to understand is I have a metal, right? I have a metal, and I'm going to give an electric arc. This is an electric arc, like basically electric pulse is what I'm going to give. A very strong electric voltage I'm going to give. Okay, so why do I call it as an arc? It's like an arc cutting it, like something like that. Okay, so anyways, it's basically what you have to understand is a strong electric voltage pulse is what I'm going to give. Okay, so what is going to happen because of this is obviously, you know, whenever voltage is passed, heat is also going to get produced, right? So because of this heat, I'm going to have some vapors of this metal, right? Metal vapors are going to be produced, right? And these metal vapors are condensed again, right, to form colloids, right? They will be condensed in special conditions, right? For obviously, right, you have to understand that they have to satisfy the particle size range that what I told you, 1 nanometer to 10 nanometer or whatever it is, right? That particle size has to be brought in, right? So the electric arc is produced. So the heat produced due to the electric arc vaporizes the metal, right? And the metal again is condensed to go for colloidal range. This is what is called as Briggs arc method. Okay, right. So these two are the methods you have to understand. Now what I have to do is the colloids formed by any of these methods, right? The colloid formed by any of these methods is not pure, not that much pure, right? So you have to go for purification of colloids, right? Once you produce them, you have to go for purification, right? So purification, there are two techniques. Actually, there are three techniques. Can you tell me what are the three techniques? Purification techniques, purification of colloids. There are three, 1, 2, and 3. What are they?
Electrophoresis, sir.
Electrophoresis is the property of the colloid. We'll come to that. No, that is not used for what is that? Purification.
Dialysis, sir.
Okay, dialysis is 1, definitely. Right? I'll just write it as 2. Okay. So first one is dialysis. Second one is dialysis. Okay, other two. A dialysis, little better version of dialysis is what is called as
Electrolysis.
absolutely. So electrodialysis. Okay, one more.
Peptization.
Sorry.
Peptization.
Peptization. Peptization. No, peptization is not this. Peptization is conversion of peptization, coagulation, flocculation, peptization. Anyways, I think what you mean is conversion of a colloid to a precipitate, suspension. That is what is called as peptization, I guess. Not this. One more. Okay, the other one is what is called as your ultrafiltration. Is it not? Right? Ultrafiltration. Ultrafiltration, what do you do? It's exactly like filtration, but you use a special filter paper called as ultrafilter paper. Right? So what is ultrafilter paper? You take the normal filter paper, right? And you dip it in solution called as collodion solution. This one all is all available in your book. Okay, so you take a normal filter paper and you dip it into a solution called as collodion solution. So then you dry it, right? And then the filter paper, what you're going to get is what is called as your ultra filter paper, right? Then you do normal filtration with whatever you have produced. So you are going to remove some impurities. Okay, right. So in dialysis and electrodialysis, if you understand dialysis, electrodialysis is very simple. Okay, right. So we'll understand what do you mean by dialysis. I think I'm taking a lot of time. Okay, so dialysis, you are going to have, okay, bear my diagrams, please. Okay, I got it. Right. So you are going to have this kind of a vessel, right? Now, please understand that this can be this is going to be a semi-permeable membrane. Semi-permeable membrane, say this can be made up of sheep's bladder. It can be nitrocellulose, anything with the semi-permeable. Okay. So now this is going to be put. This contains the colloid, right? And then this is put in another bigger vessel, which is going to contain, say, water. Okay, right. Now, what you have to understand is what are the kinds of impurities we have in colloidal solutions. We are going to have the impurities in the form of another ions, right? Say, for example, it's a silver salt, right? Say I might have some sodium ions, chloride ions, or magnesium ions. So, excuse me. So on and so forth. These are going to be the impurities. Okay. So what is going to happen? Through a semi-permeable membrane, I can have osmosis can happen. What is osmosis? Osmosis is movement of solute particles from a region of higher concentration to the region of lower concentration. Obviously, now this is the higher concentration side. Outside is lower concentration. Concentration of what? Concentration of the impurities I'm talking about. Concentration of the ions, which are the impurities. Okay, so what is going to happen? Through this semi-permeable membrane, right, the ions are going to come out. Right, the ions are going to come out because here I have low concentration, here I have higher concentration. By that, you will be able to remove the ions. Okay, right, fine. But again, what you have to understand is after a point of time, say after some 3 hours or 6 hours, depending on the quality of this thing. Yes, any doubts? Okay, I suppose no, nothing. Okay, so what you have to understand is after a point of time, right? So this solution which is outside is going to have so much amount of ions. Now, please understand, people, the difference in concentration here. Here I have if at all I have very high concentration, here I have very low concentration. If the difference in concentration is high, as long as the difference in concentration is high, then you will see efficient movement of particles from inside to outside. Right, but what will happen as the time progresses? They will try to attain equilibrium, in the sense that the concentration inside and the concentration outside will become almost similar, almost same. Now, obviously, no diffusion will happen or no osmosis will happen. So what you have to do, after each and every, say, 3 hours or 6 hours, you have to change the water outside. Okay, you have to remove this and I put fresh water. So what is going to happen? Obviously, now again you give a huge concentration gradient, concentration difference between inside and outside. So again, the osmosis will happen. Okay, right, fine. Now, okay, now the better, again, obviously, you have to understand that it is going to take a lot of time. Dialysis is a very time-taking process. Okay, so in electrodialysis, what we'll do is we're just going to have 2 electrodes inserted, and I'm going to give a power supply as simple as that. Right, now, why is this gonna help? This is going to help because all these ions are charged particles, positive ions and negative ions. So if I'm going to include an electrode towards the positive electrode, the negative ions are going to move faster, right? And towards the negative electrode, the positive ions are going to move faster. Thereby, I increase the speed at which the dialysis happens, and that's why we go for electrodialysis. Very, very simple. Similar mechanism. Just by putting 2 electrodes in the solution, you are going to increase the rate of dialysis. That's all you're going to do. That is what it is called as electrodialysis. Okay, so these 3 are what are your purification techniques for purification of colloids. Okay, fine. So you understood what are colloids, how are they prepared, how are they purified, and the last part, what you have to understand is the properties of colloids. Okay, so properties of colloid. The first one is what is your famous Tyndall effect, right? So Tyndall effect, we all know. If you're able to see the path of light moving through the solution or moving through a particular substance, that is what is called as Tyndall effect, and that happens due to scattering of light rays by the particles, right? And why is it that the true solutions are not able to give Tyndall effect? Why? And colloids are able to give Tyndall effect. Why is it like that? Why true solutions will not give Tyndall effect, but colloidal solutions will give Tyndall effect? Why? Random arrangement? No, that's not the answer. Yes. This kind of question also can be asked. Why colloid shows Tyndall effect while true solutions does not? Explain. It is all because of the particle size, right? So please understand, Tyndall effect is just the scattering of light, isn't it? So if the incoming light is coming, only if the particle is little big enough, this scattering can happen, right? If the particle is so small, the wave will be just able to bend it and just move away. I'll not be able to see the scattering rays. The light ray is not going to get scattered if the particle size is very small. Okay, so the answer to this question is just the particle size. The colloidal particles are a little bigger compared to the wavelength. If you want to compare two things, you can compare the particle size with the wavelength of the light used, right? If the wavelength is smaller compared to the particle size, big particle, then scattering can happen. But in the case of true solutions, we know the particle size is very small, right? So this particular scattering will not happen in case of true solutions. Okay, right? So that's about Tyndall effect. Then we move on to Brownian movement. So Brownian movement, for your level, what you have to understand is everything possesses kinetic energy, right? All the colloidal particles possess kinetic energy, and they will be in random zigzag motion, as your NCRT book calls it, right? So it's all about the zigzag random motions undertaken by the colloidal particles because they have kinetic energy. That's it. That's all you need to understand, right? They'll be in constant random zigzag motions. Okay, fine. The next thing is what is about the charge, right? Charge of the colloidal particles, right? It's pretty easy to understand, people. Say I contain an FeCl3 colloid, a salt, right? FeCl3 colloid. Now, to this, I add excess of Fe2 plus. I add excess of iron salt, right? What is going to happen is this is the colloid, assume, right? So if you're going to add more amount of Fe2, obviously what will you understand is on the surface of each colloidal particle, you are going to have some amount of positive charge present. Okay, now instead of more amount of Fe2 plus, if you add more amount of say Cl minus or I minus, then you will see negative charges getting formed on the surface of the colloid. Okay, right. So now what is going to happen? This cannot stay as such, right? This cannot stay as such. So what is going to happen? If the first layer is a positive charge, it is going to attract negative charges towards it. Is it not? So there'll be a first layer of positive charge, second layer of negative charge, like this, right? This is what is called as Helmholtz. Helmholtz? What? Helmholtz?
Dielectric.
Okay, Helmholtz dielectric, or it is called Helmholtz double layer. Okay, right? So Helmholtz double layer is on because of the charge possessed by the colloidal particle surface, and then on top of that, the opposite charges are going to come. Right now, obviously, what you understand is this area. This is one field, and the negative charge is another field. Right. So obviously, there will be some potential difference here between the positive, between the first layer and between the second layer. You will have some potential difference, and that potential is what is called as
Zeta potential.
absolutely, that potential is what is called as zeta potential. These are some words you need to you have to know. Questions will come from this only. Okay, the potential difference between the two layers of the colloid, two charged layers of the colloid. The potential difference is what is called as your zeta potential. Okay, right. But what you have to understand is this: the second layer is not as strong as the first layer. Second layer will be very much diffused, very there and there hanging kind of stuff. Easy to remove. But the first layer is a little difficult. Okay, right. So that is about. So we saw three stuff: Tyndall effect, charge, and one more we saw. What is it? Tyndall effect, charge, and one more was Brownian movement. Okay, we saw three things. Okay, and obviously now you understand that because of this charge, I can have one more property, and that is what is called as your electrophoresis. Right? Electro means obviously charge, electrons. Phoresis means movement. Right? So if you apply some electric field, if you put an electrode and apply some electric field, voltage you apply, because of the charges like this, these colloidal particles can move. Right? So the movement of colloidal particles when an external electric field is applied, that phenomena is what is called as your electrophoresis. Okay, right? So again, you just have to know the definition. Nobody is going to ask you a full length explanation for all of that. You just have to know what is electrophoresis, what is zeta potential, what is Helmholtz double layer, like all the keywords. The definition is what you have to understand. Okay, so that is about the charge and stuff. And then obviously you can easily convert a colloid to a precipitate, and that is what is called as coagulation. Right? So how will you do it? Is very easy for us to understand. Right? Now when a colloid is there and you add some amount of electrolytes, right? This is going to form precipitate. I think this is what is, I think, something someone said as peptization. I'm not wrong. Okay, the addition of an electrolyte to a colloid to convert it into a precipitate, right? That is what is called as coagulation, or it is also called as peptization. I don't know whether it's correct, but it's something someone told. But even I have somewhere heard it, right? Okay, so this is how you convert into a precipitate. Now, what is the role of the electrolyte here? How is the electrolyte able to convert a colloid into a precipitate? Is a nice question you can ask me, right? So it is all about again the charge. Right. So I told you that the second layer is not that important. We forget about the second layer, but the first layer, assume that it is positively charged. Right. Now, say if I add a negatively charged electrolyte, for example, say you use NaI. Okay, forget about Na plus. Na plus is not going to have any effect here, but the I minus will come and attack here. Then this is going to get distorted. Right, this is going to get distorted, and by that I will be able to convert this colloid into a precipitate. Okay, so basically the role of the electrolyte is to give the oppositely charged ion. Opposite to what? Opposite to the charge of the colloid. Right, the electrolyte has to supply an ion which is oppositely charged to the charge of the colloid, and that is how I'll be able to convert them into precipitate. Okay, right. So now there is something called as flocculating power. Right, what do you mean by flocculating power? Basically the coagulating power. Coagulating power means which electrolyte will have more power, right, to convert a colloid into a precipitate. They would have given you some definition also. Flocculating power is defined as the amount of electrolyte required to convert, I think, 1 gram of the colloid into a precipitate. Some definition will be given. Just look into it. Basically, it talks about, like, say, if I consider NaI with, say, sodium sulfate. So I'm just giving you an example, right? Which will have more effective conversion of colloid to precipitate. That power is what is called as your flocculating power, right? So the flocculating power or flocculating value is going to be directly proportional to the charge of the species. For example, assume that I have a negative charge on the surface, right? Say if I'm going to add two things, say I add NaCl and if I add NgCl2, right? I know I'm going to get Na plus and Ng2 plus from this. Again, Cl minus has no role to play because this is negative. Correct, right? So obviously what they say is Mg2 plus will have more flocculating power than Na plus, because more and more, that is what is called as what rule? That rule is called as what rule? this flocculating value or flocculating power directly proportional to the charge of the electrolyte species, what is the rule called as? What is the rule called as? It's called Hardy-Schools rule, right? So I think this is all there in NCRT. I'm not telling anything new. I'm not telling anything out of NCRT. It's all there. I'm just telling what is there. Okay. So yeah, and then what you have to understand is about the applications of colloids in gas mass, so on and so forth. So many applications. There'll be so many points will be given, right, in the last part of the NCRT this chapter. So that you have to again look into. Okay, any questions? Any questions from this chapter? And that's it. That's about colloids. Okay, I suppose there are no questions, right? Good. So then now we'll move on to electrochemistry. Okay. So electrochemistry, is going to have a lot of problems. So we have to solve a lot of problems, guys. So please sit with a notebook and a pen. And there'll be a lot of theory questions also. Right. Okay. Okay, please take down the question. I'm going to give you a question. Please take it down. I'm going to dictate it. An electrolytic cell filled with an electrolytic cell. Please, everybody do copy. Everybody, please do try the problem. It's all for your practice only, right? Okay, I have no gain in doing this. Please, for you only we are doing. Please do it. Okay. So what I was telling, an electrolytic cell was filled with 0.1 m KCl solution, capital M, 0.1 capital M KCl, and it has a resistance of of 85 ohms, and it has a resistance of 85 ohms and specific conductance of 1.29 into 10 to the power minus 2 Simon. Okay, so the resistance is 85 ohms and the specific conductance is 1.29 into 10 to the power minus 2 Simon. Okay, right. Now the question continues. When the same cell was filled with 0.05 m, capital M, when the same cell was filled with 0.05 m, capital M, of an unknown electrolyte, is filled with an aqueous solution, is filled with a 0.05 m solution of an unknown electrolyte. This is another electrolyte. We don't know what is electrolyte. Doesn't matter, right? the resistance was 96 ohms. The resistance was 96 ohms. Okay, right. Now what they're asking is find the molar conductance of this unknown solution. Find the molar conductance of this unknown solution. Okay, right. I'll repeat the question. So if at all there was a a certain an electrolytic cell was filled with 0.1 mkcl and it has a resistance of 85 ohms and specific conductance of 1.29 10 to the power minus 2 Simon. When the same cell was filled with an aqueous solution of 0.05 m unknown electrolyte, the resistance was 96 ohms. 96 ohms. They're asking what is the molar conductance of this unknown electrolyte. Please solve the problem. I'll give you 2 minutes. Or at least if you don't like, we don't have to spend time on calculations. At least tell me how will you do the problem. Yes. What is the formula we have to use? How do we use the problem? So look at the question. They have given you an electrolytic cell. Initially, there is amount of KCl. So they found out the resistance, right? And they also found out the specific conductance. What is specific conductance? What do you mean by specific conductance? What is specific conductance? Specific resistance means what? Hope you're all there, right? I see 1, 2, 3, 4. 4 people. Specific resistance is what? Resistance? Specific resistance is what then?
Resistivity, sir, rho.
Thank you. Right, that is resistivity. Same way when I say specific conductance, what is this then?
Conductivity, sir, kappa.
That's it, right? Kappa, conductivity, K value is what is given to you. Okay, right? So what I understand is 0.1 mkcl. They have given you my R value. R value is some 90 ohms. 90, 85. Okay, 85 ohms. And they have given you the K value. K value is what? 1.29 10 to the power minus 2 Simon. This is given to us. Okay, it's not Simon, it's Simon. It's given as Simon per centimeter. Please change it. Simon is for conductance. Okay, sigma. That is 1 by ohms is what is mho. Mho is also called as Simon. Right? Okay, so the conductivity value is 1.29 into 10 to the power minus 2 Simon per centimeter. And what they're asking, I have a 0.05 m some X solution. I don't know what it is. I don't even want to know what is that. All I want, they have given the R value to be 96 ohms, and they're asking molar conductivity or molar conductance, that is lambda m. Is it not? What is the formula for lambda m? Formula for lambda m is what? Come on, I know you know it. Tell me. Lambda m formula is what? Molar conductivity's formula. So I should take that you don't know this. Come on, guys, you should know it. Like, you have written so many exams. This is a very important formula. How come you don't know it?
Sir, kappa with molarity, sir.
Thank you so much. So it's basically K by C, right? Concentration is basically your molarity, is what you have to understand. Okay, and it's not very simple, guys. Please understand, for lambda m, you will write it in Simon centimeter square per mole. No, sorry, mole power -1. That is what you. That's how you'll write. Okay, Simon centimeter square per mole will what will the unit. Now, if you see that this is in Simon per centimeter, right? All you have to do is multiply this by 1000, divide by 1000 or multiply by 1000, divide by 1000. Correct? Yeah, divide by 1000. Right? You have to divide it by 1000. This is the formula you have to understand. If you want the answer, if you want the lambda m in with Simon centimeter squared per mole, right? And if K value is given in terms of Simon per centimeter, you have to put 1000 in the denominator. Okay, this is the formula you have to know. Okay, fine. So obviously they have given me R. So for me to find lambda m, I require K. How will I find it out? Right? For that, you need to find out something else before that. What you have to find? Conductivity cell or electrolytic. Did they say electrolytic cell? Oh, sorry guys, it's a printing mistake. It's not electrolytic cell. It's a conductivity cell. Please change it. Okay, there I told that a certain electrolytic cell, but it's a printing mistake. It's not electrolytic cell. It's conductivity cell. Okay, a conductivity cell is there. First 0.1 m KCl and then this 0.05 m unknown solution. Okay, right? So conductivity cell, what is the formula? Conductivity cell, will be something called as, for a conductivity cell, there'll be a constant. What is the constant? You know how a conductivity cell works. Everybody knows. How will you find out resistance from that? So you can be frank that, sir, I don't know. Can you please teach? I'll be glad. But if you're not going to say anything, I really don't understand what is happening. Can you please speak up? Do you know or you don't know? You want me to teach? What happened, guys? Is there a problem? I still see 4. Is everything okay? Okay, I don't understand what is happening. Okay, fine. So the formula which you have to understand is R into K is G star. This is the formula you have to understand for conductivity cell. Right? This G star is what is called as your cell constant. Right? G star is what is called as your cell constant. Okay, this cell constant is determined by what? This cell constant is nothing but L by A, length of the conductivity cell divided by area of the conductivity cell. Right? I think you know all this. I don't know what happened. Anyways, so this G star is what is called as your cell constant, and that's nothing but L by A. Okay, right. L is the length of the conductivity cell, A is the area of the conductivity cell. Right? Fine. Now they have mentioned you in the question that there, for both these 0.1 m KCl and the 0.05 m of the unknown solution, right? They are using the same conductivity cell. That means they will have same G star. Okay, they will have same G star. Correct. Okay. So now, if I can find the G star here, that G star can again be applied here. Again, that same G star will be equal to R into K. R is given to you for this. K can be found out, and that K can be substituted here, and lambda M can be found out. Again, I repeat, right? So you see R and K both are given, right? So if R and K both are given, the G star can be calculated. G star is the cell constant, right? And we are using the same cell for both these experiments, right? So if I'm going to use the same cell, obviously same cell constant will be there. So that G star can be used here, right? Now they have given R and they're asking you what is lambda M. For lambda M, we need K and C. C is known, 0.05, not an issue. K is what we don't know. So we again use the same formula, G star is equal to R into K, right? R is given, G star we calculated, K can be found out, substituted here, and lambda M can be found out by this formula. Everybody understood? Can you please give me, everybody can give me a yes that you can do? Guys, did you understand? Yes, no? Okay, 1,
Understood, sir.
2. How many are there? Yeah, 2 more. Okay, fine. Cool. So this kind of question is very famous in board exams. Okay, so the calculation you can do it later. Okay, fine. We'll go to the next question. And guys, please open up. If you are not going to do it, there is no point in me teaching you. Okay, right? Fine. Next question. Okay, go to the next one. Fine. So they have given lambda M of CH3COOH at some concentration is 11.7 Simon centimeter squared per mole, and they have given lambda M naught of CH3COO minus as 40.9 Simon centimeter squared per mole, and lambda naught of H plus is given as 349.1 Simon centimeter squared per mole. So what I need to know is degree of dissociation, that is we know is alpha, of CH3COOH is what? Okay, right? Lambda M value is given, lambda M naught of CH3CO minus and lambda M naught of H plus is given. All they want to know is the degree of dissociation alpha of CH3COOH. How will you do the problem? Tell me.
So we need to add the lambda m naught value, sir. 40.9 and
Okay. Why we have
349.1.
to add? Is there any law?
Yes, sir. Cortex law.
Okay.
That the lambda m naught value of CH3COH is the addition of both of these.
Okay. Okay.
And then for alpha, we need to divide lambda m divided by lambda m naught, sir.
Okay. Correct. Right. Good. So Kohlrausch's law is what we have to use here. Kohlrausch's law states that for the limiting molar conductivity of lambda m naught is limiting molar conductivity. Limiting molar conductivity is molar conductivity at infinite dilution or zero concentration. We write it as lambda m naught, or we write it as lambda m infinity. So lambda m naught means zero concentration. There is zero concentration, and what is that? Infinity represents infinite dilution. Okay, so what Cortex's law says is that limiting molar conductivity of any electrolyte is equal to the sum of the limiting molar conductivities of its constituent ions. That means what? We can take this as the example. Lambda m naught of CH3COOH is equal to lambda m naught of CH3COO minus plus lambda m naught of H plus. This is what the Cortex's law says, right? So now there's only one formula. Alpha is equal to lambda m divided by lambda m naught. This is the formula which you know, right? So lambda m is already given. Lambda m naught, you just add lambda m naught of CH3COOH. You add these two by Cortex's law. You get this and then substitute. Very simple problem. Okay, right? Fine. Next question. Okay, now we'll speak more about this. Some theoretical questions can come from this, right? So they'll ask you to explain. Okay, fine. If you have, it's pretty easy, right? I hope I can drop this. Two formulas, this and that's it. Okay, so theoretical questions can be, they will ask you to draw a graph, like say the graph you know is between lambda m and root c, right? Lambda m and root c. If you plot a graph, right, what you're going to see? You are going to see two different kinds of graph for two different types of electrolytes. One for strong electrolytes and the other one is for weak electrolytes. You will see that for strong electrolytes, you'll be a straight line, right? And for weak electrolytes, you'll see that there is going to be this kind of curve, right? A curve is going to be there, but for a strong electrolyte, this is for strong electrolyte, and this is for weak electrolyte. Okay, now you have to understand why this kind of stuff happens, right? Fine. Now, what I see in both these cases, what I see in both in the case of strong as well as weak electrolyte is that as I increase the concentration, the lambda m value decreases. Now, it's very straightforward for us to understand. You can look at the formula. Lambda m is equal to K by C. Is it not? So if I increase the concentration, the lambda m value is supposed to decrease. This is by mathematics. You can see, right? Or if you look at in terms of logic, the concepts. And now, when I'm going to have more amount of, like say, a high concentration, if I'm going to have, right, the mobility of the ions is decreased, right? The mobility of the ions is decreased. Now, please understand lambda m, right? Lambda m is basically based on both conductivity as well as the concentration, right? Now, if I'm going to increase the concentration, the ability of the ions to move, that is what is basically the conductivity, is it not? Right? That is based on the mobility. Since these charged particles are able to move through the electrolyte, that is how it is able to conduct electricity. Correct, right? So if I'm going to have very high concentration, all these ions are very, very close by each other, so they will not be able to move that much, right? Their mobility is decreased. Because their mobility is decreased, their conductivity value is also decreased, right? And obviously you see that the lambda m value also decreases. Okay, so either way, what you have to understand is if I increase concentration for both strong as well as weak electrolytes, you are going to have decrease in lambda m value, right? Okay, now next thing what you have to understand is why is there a difference in graph? One is, you see, as I increase the concentration, there is a sharp decrease in the lambda m for strong electrolytes, right? And you see the pace at which, the rate at which the lambda m decreases for weak electrolytes is very slow. It's very slow for weak electrolytes. Again, it's very simple, right? Now, how we understand this? Now, let me go from this side to this side, right? So this side to this side, that is from left to right, I am increasing concentration. So from right to left, right, what I'm doing is decreasing the concentration, or I would say that I am increasing the dilution. I'm adding more and more amount of water, right? Okay, so now what is going to happen? Now, when I add more and more amount of water, when I'm going for more and more amount of dilution, as you add more and more amount of water to a strong electrolyte, the ionization keeps on increasing. Right? NaCl, if you take little amount of water, okay, little dissociation, more amount of water, more amount of dissociation. So it is very linear, right? So the more and more amount of water you add, the dissociation is going to keep on increasing, right? And that is going to be very effective in case of strong electrolytes. But you know, weak electrolytes will not ionize that much, right? So you have to add a large amount of water for me to have considerable increase in the dissociation. For a for a small dissociation, you have to add a large amount of water in case of a weak electrolyte. That is why you see the change is slower in case of weak electrolytes, but the same thing is faster in case of strong electrolytes. Okay, right? And this is where your Cortex law comes into the picture also. Say now, if I want to find what is the lambda m value at zero concentration, now what I do, I can just extrapolate this graph for a strong electrolyte, and this is what is my lambda m naught or lambda m infinity, right? But for weak electrolytes, you will not be able to do it because they might not meet at all the y-axis, right? So that is where the problem comes, and that is where we go for Cortex law. Okay, now there is something called as your Debye-Huckel equation or Debye-Huckel-Onsager equation, and that is for strong electrolytes. From the graph itself, you can see basically I'm going to have y is equal to mx plus c. What is y? Y is lambda m. What is x? X is root c. M, some m. We'll just skip. We don't know what is the slope, and I know what is the intercept. Intercept I see here is lambda m naught. So this is what is called as your Debye-Huckel-Onsager equation. Okay, right? So that is all about molar conductivities and limiting molar conductivities, right? Okay, fine, we'll continue. Right, moving on. Okay, so the question goes like this. An aqueous, take down the question, guys, please. Right, an aqueous solution of copper sulfate. An aqueous solution of copper sulfate was electrolyzed. An aqueous solution of copper sulfate was electrolyzed using a current of 0.1287 amperes, right? The aqueous solution of copper sulfate was electrolyzed using a current of 0.1287 amperes for 50 minutes. For 50 minutes. Okay, so they have to know, they want to know what is the mass of copper deposited. What is the mass of copper deposited? Okay, right? So Okay, can you tell me which area this question is from? From the chapter, which area, which say the which portion of the chapter this question is from? What? Where is this question from? Which part of the chapter? Nobody knows. This is not from Faraday's first law. Okay, so tell me what is Faraday's first law? Can someone tell me the exact definition of Faraday's first law? Faraday's first law. Come on, guys. Faraday's first law. I know. At least one of you should know it. Nobody knows Faraday's first law, and you have written so many exams. Okay, right. So Faraday's first law says that the quantity of electricity, or say that starts with the amount of substance deposited, right? The amount of substance deposited at any electrode, right, is directly proportional to the quantity of electricity passed through the electrolyte, right? Basically what it says is the mass of substance deposited, M, is directly proportional to the quantity of electricity. Quantity of electricity basically means charge, right? Quantity of electricity, that is means what? Charge. So M is directly proportional to charge. That's what it says. The more and more electricity you pass, more and more charge you pass, more and more will be the amount of substance getting deposited, right? Okay, so now for removing the constant, we write so I know charge Q is equal to I into T. So M is directly proportional to I into T. So M is equal to Z into I into T. And this Z is what is called as your electrochemical equivalence. Right? Okay. But we don't have to use the formula. There is another method of doing this kind of problem, whatever the problem I gave you now. Right? Now it's very easy. Like you just have to use the stoichiometry. Okay, fine. So this is what is Faraday's first law, and this is the equation concerning it. But we can directly use this formula to find it. If you want to use this method, please go for it. You have to find the Z, I is given, T is given, right? Or you can use the method which I am going to follow now. That also we'll see how to do it. Okay, so this is fine, right? So first things foremost, whenever you talk about electrolysis, right? Whenever you talk about electrolysis, always you have to go for reduction of the metal, right? Reduction of the metal means you have copper sulfate, means I'm going to have copper 2 plus ions, right? Will accept 2 electrons to form copper. This you have to write. If at all if they have given me aluminum sulfate or aluminum chloride, then I would have written Al3 plus 3 electrons will give me Al solid. This is how copper is getting deposited. You know how hopefully everybody knows how an electrolytic cell works. So this is what is my electrolyte, or say for example, this is famous example we'll take as NaCl solution I have, right? Now I need to have 2 electrodes dipped here, right? Say one is negative, positive, negative, positive. Negative is what is called as cathode. Positive is what is called as anode. Right now, when you switch on the battery, what is going to happen? I have Na plus ion and the Cl minus ion present in the solution, right? So the charged ions are going to move towards their oppositely charged electrodes. That means a positive charge will move towards a negative electrode, and a negative ion will move towards the positive electrode. Very simple. That is, opposite charges are attract. Correct. So Na plus is here. Na plus will move towards the cathode because that is only negatively charged. So at cathode, what will you see is Na plus moving towards the cathode, and you see it is connected to the negative terminal of the battery. That means it is going to have, it is going to be rich in electrons. It is going to have higher amount of electrons. So what is it going to do? Na plus is positively charged, so it is rich in electron. So this cathode is going to donate one electron to Na plus, right? So it will donate one electron to Na plus. So you'll form sodium solid, sodium metal will be formed. Same way at anode, what will happen? Cl minus is there. Cl minus is negatively charged, so it is going to move towards the positive electrode. That is my anode. And you see anode is going to the negative positive terminal of the battery, and Cl minus contains excess electron. So it is going to donate electron to anode, or I would say anode will remove an electron from Cl minus. Right? So what? How will you write the equation? 2Cl minus will form Cl2 by losing 2 electrons to the anode. Okay, now what I've seen in galvanic cell, anode oxidation. Same way here also, anode oxidation, cathode reduction. Same thing only will happen. See, you see, at cathode reduction is happening. Sodium plus becoming sodium. Here you see Cl minus becoming Cl2. It is oxidation in anode. Right? So you can understand this is qualitative way of understanding. Now, depending on how much power supply, how much electricity you pass, accordingly, I will be able to get more and more amount of sodium or more and more amount of chlorine. That is what your Faraday's first law says. Okay, right? This is the basic understanding of an electrolytic cell. Right? Okay, cool. So moving on, right? This and all are not important for us. We just have to solve the problem. Okay, so any kind of this kind of problem is given to you, or they're asking you to find the amount of substance deposited. You first write the reaction, okay, with respect to the electrons and all you involve, and you write the reaction. Okay, fine. Then what you do is they have given this, that is your, right, the current value and the time value. Right, so I can easily find the charge. Right, charge is equal to q I into t. Q is equal to I into t. Right, so that would be 0.1287 into 50 into 60. I have to put it. Please understand, you should do convert into seconds. SI units you have to do. If you don't do it, the entire problem is wrong. Okay, so please understand that q is going to be, sorry, it should be in seconds. Whatever they give you, you should convert them into seconds and then only do the problem. Okay, right. So this you have calculated. Then what you do is, now I told you that we are going to use stoichiometry, right? Stoichiometry means what? Here you see the number of moles of electron here is 2 and the number of moles of copper deposited is 1. That means what? For depositing 1 mole of copper, I require 2 moles of electron, right? So if I can find what is the number of moles of electron, I will be able to find what is the number of moles of copper formed, and from the number of moles of copper formed, I will be able to calculate what is the mass of copper deposition. Okay, now the next question you'll ask me is, sir, how do I find the number of moles of electron? It's very simple, guys. I'm going to give you a formula. N, number of moles of electron, is equal to Q, that is, okay, I'll write it as Q divided by F. Right, number of moles of electron is equal to Q divided by F. You know what is F? How do you define 1 Faraday? What is 1 Faraday? I'm not asking you the value. What is the definition of 1 Faraday? What is the definition of 1 Faraday? 1F means what? Okay, what is the value of 1F? What is the value of 1F? What is the value of F? F is a constant. What is the value? Approximate value. Are you guys tired? I don't think you had school also today. Did you have school? Okay. So this is going to be taken up. Since you're not responding, I will see what I can do. I'll take it up with the management. This kind of classes I don't really encourage. Okay. Fine. So I'll complete this problem and it'll wind up. Right? Okay. So what I was telling is, yeah. So this is the formula to find the number of moles of electron, Q divided by F, and F is nothing but charge of 1 mole of electron, right? 1F is charge of 1 mole of electron, right? We know what is the charge of 1 electron. 1 electron's charge is 1.6 and 10 to the power minus 19 coulomb. This is charge of 1 electron. And if I say 1 mole of electron, in 1 mole of electron, I know I will have Avogadro number of electrons. That is 6.023 into 10 to the power 23 number of electrons are there in 1 mole of electron. This is not you have studied in 11th class, mole concept, right? So if I say 1F, F I say that the charge of 1 mole of electron. So this into 90, sorry, this is charge of 1 mole, sorry, charge of 1 electron. I have to multiply into the number of electron, and the number of electron is Avogadro number. So that 6.023 and 10 to the power 23. So approximately, you will find that the F value is 96,500. Okay, right. So number of moles of electron can be calculated. Q divided by F. Q we calculate I into T. F value we know is 96,500. Right. So now you will get the number of moles of electron. Okay. So after finding out the number of moles of electron, then the problem is very simple. Now you see for 2 moles of electron, I get 1 mole of copper. Right. So whatever the number of moles of electron, whatever you get, that number of moles of electron divided by 2 is what is going to be my number of moles of copper. This is from stoichiometry. 2 moles of electron gives 1 mole of copper. So n number of moles of electron will give me n by 2 moles of copper. Very simple. Right. Now you know the number of moles of copper. This number of moles of copper into 63.5. 63.5 is nothing but the molecular mass of copper. Right? You multiply it, you are going to get the mass of copper deposit. Okay, fine, guys. We'll see what we can do. I'll talk with the management. I don't know why this is happening. So, anyways, thank you so much. We'll meet again.